In this lecture, we're going to talk about the so-called shock waves. What is a shock wave? Well, in studying the Doppler effect, we look at the case where the source is moving while emitting a wave. And what happens is that as the source moves towards the observer while emitting a wave, the wavelength gets compressed, so you will hear high frequency. But even though the wave does get compressed, the source actually still moves slower than the wave itself. Okay? What happens when the source moves even faster than the wave that it emits? The situation becomes more interesting in that case. Well, take a look at these two pictures. In a picture on the right, on the left, you have a duck that's paddling slowly over the surface of the water while creating a water wave on the surface. Here, obviously, the duck moves slower than the wave it creates, so you see ripples both in front and behind. Okay, and V source here is the duck, and that's slower than the speed of the water wave V. But in the second case, the duck's swimming faster, and you see a cone-shaped region where there's a ripple trailing behind. Okay, and you see nothing in front of the duck. You don't see any wave in front of the duck. It's because the wave doesn't move as fast as the duck, so therefore it cannot move ahead of the source, which is the duck. Okay, that's when source Vs, the speed of the source Vs, is faster than the wave, speed of the wave it creates. In fact, the second case is an example of what's called shock wave. I mean, it doesn't sound like, it doesn't look like something shocking, but that is actually the same idea. Anytime when the source that creates a wave travels faster than the wave it creates in that medium, you have what's called a shock wave. Okay, so here is a diagram that illustrates the region in which the shock wave exists. Now, suppose I have an airplane that starts out from here, from this point, moving along the positive x direction, while at the same time emitting a wave. Okay, as it breaks through the air, it creates a wave which propagates in circles centered at where the wave is first initiated. So at a certain initial moment, a wave is created while the airplane is at position number 4. So you see a big circle of the wave coming out. Okay, that circle has the biggest radius, and that circle is labeled number 4. So time t later, the circle becomes this big, okay? But at the same time, during the same time interval t, the airplane itself has already broken out of that circle because it flies faster than the circle, than the wave it creates. So the wave has reached forward to this position, okay? But the airplane has moved to point B ahead of that. Right? Because the airplane flies faster than the wave it creates, which means it's faster than the speed of sound. Okay, now during this whole time, the airplane keeps on creating more and more waves, except those waves are created later. So therefore, they didn't have as much time to travel. So the circle or the sphere they created would have smaller and smaller and smaller radius. All right. So here is, for example, a circle that is smaller. It started out at point number 1. That's the center of that circle, point number 1. It didn't have much time to propagate. So so at the moment this picture is taken, the circle has a smaller radius. Okay, and then by the time the airplane reaches point B, this is the moment this picture is taken, and a wave has just been created by the airplane. It doesn't have a chance to travel yet, to propagate yet, so the circle just reaches the dot at point B. Okay, now you can imagine this is only a cutaway, a 2-dimensional cutaway. The actual situation is actually 3-dimensional, so you can imagine if we take this region, we take this region here, okay, and we rotate about this axis, you can get a symmetrical 3-dimensional structure that is, of course, in the shape of a cone. And within this cone, you got waves already propagating. Okay, that's already propagating. So let me highlight this region. So this is the region in which the wave is already reached, but outside that region, clearly there is no wave yet. Okay, so what you have here is a leading edge. This is a leading edge of the wave. All right, so inside that cone, wave has already reached. Outside, there's nothing, right? And so this is a case that we didn't see before if the speed of the wave is faster than the source, because if the speed of the wave is faster than the source, in this case, the airplane, you will see waves in front of the airplane because the wave created by the airplane flies faster than the airplane itself. Okay, that's when the airplane flies slower than the speed of sound. But in our case, the entire profile of the wave it trails behind the airplane because it cannot reach the same speed as the airplane. All right, so this cone is the so-called shock wave. Okay, the wave inside this cone is so-called shock wave. And we can even calculate this half angle of that cone. Between points A and B, the wave traveled between the airplane traveled between points A and B. So AB, the length AB equals the speed of the airplane, V source times T. T is the time it takes for the airplane to go from point A to point B. But in the meantime, the wave that was originally created at point 4, right here, has now had the same time to travel. So therefore, it moves out by a distance of AC. Okay, this wavefront has reached point C, and that equals V times T. V is the speed of sound, and which is less than Vs in this case. Okay, now this line here, which is the leading edge of the wave, which is known as a wavefront, is certainly perpendicular to the direction of propagation of the wave. Okay, so we're looking at a 90-degree angle here, and the 90-degree angle here. So in the right angle triangle ABC, what do I have? I have sine theta equals what? Equals AC over AB. AC over AB. Okay, but AC equals VT and AB equals V source T. So therefore, you cross out the T, you get V over Vs. And this tells me how to find the angle theta. Theta is the inverse sine of V over Vs. Okay, so you see this whole thing only makes sense if V is less than Vs, because otherwise you get a value of a sine function greater than 1, which is impossible. Okay, so this happens if V source is greater than V. So the thing flies at supersonic speed and you get a shock wave. And the greater Vs is, the smaller the angle. Okay, so you're basically concentrating all the waves within this very narrow cone if you fly at a speed far greater than that of sound. Okay, and we're not limiting ourselves to to an airplane flying through air in supersonic speed. Anytime the source travels faster than the wave it creates, you're gonna get yourself a shock wave. And we see, in this case, the duck travels faster than the water wave it creates, and you have yourself a shock wave. Okay, so why is the shock wave important, and how is it different from a conventional wave? Well, we already saw, from these two pictures of the duck, in a conventional wave, the wave arrives before the source does, because the wave travels faster than the source, and you got the wave traveling in all directions. Okay, the wave is not concentrated, right? But in a case of a shock wave, for the picture on the right, the wave is concentrated in this cone-shaped region, and if you are here, if you are an observer here, there's no disturbance. Okay, and then all of a sudden, when the duck reaches this point, then the front of the shock wave will pass over you, and you're going to suddenly get a disturbance. Okay, so there's a sudden onset of that shock wave if you are an observer. Unlike conventional wave, it comes in gradually. There's no sudden onset. Okay, that's something to keep in mind. And here is an illustration of a supersonic jet flying overhead. Let's say the supersonic jet is right here, right above you, and so you are an observer and you are here. Okay. Now, when you watch, when you raise your head, you're going to see this jet right above you. But do you hear anything at this point? Well, the answer is no, because the entire wave is concentrated within this cone-shaped region, right? And we're talking about this cone-shaped region right here. Okay, you're outside of it, you don't hear anything, right? And then later on, when the airplane flies past you, at some point, you are going to hear the onset of this shock wave. As a matter of fact, in this drawing, this guy, there's a question mark overhead because this guy does not hear anything. Okay, so he sees the airplane but doesn't see anything, doesn't hear anything. This guy here, yeah, he hears something, and this guy here also hears something. In the case of the airplane, when the airplane breaks through the air at very high speed, the head of the airplane here is going to compress the air. Okay, but as the airplane flies through the air very fast, it's going to leave behind a region where there is less air than normal because the airplane pushes the air away, right? And but you say, oh, but what about the surrounding air coming in to fill the void? The surrounding air coming to fill the void. Guess what? They don't travel as fast as the airplane. Okay, so the void that's left by the airplane doesn't get filled up by the surrounding air. It's going to take some time to do that. So you have a high pressure region in front of the airplane and a low pressure region trailing the airplane. And therefore, as the airplane flies over, your ear will experience a sudden change in air pressure from high pressure to low pressure. Okay, so around here, the pressure is higher than usual. Over there, the pressure is lower than usual, and it's a sudden onset. When there's a sudden change in the air pressure passing by your eardrum, you're going to hear a sound, and that sound is very sudden. Therefore, it sounds like an explosion. Okay, actually, two explosions. One here and one here, both corresponding to a sudden change in air pressure. Okay, so that's the so-called twin sonic boom. And that is really caused by the head and the tail of the airplane flying overhead at supersonic speed. Some people say, oh, it's the sonic boom happens when an airplane breaks the sound barrier, and that is it moves past the speed of sound. No, that is wrong. You don't have to, it doesn't have to be at the moment it passes by the speed of sound, okay? Anytime something flies at any speed faster than the speed of sound, it's going to create a shock wave, okay? You don't have to be right passing the speed of sound, but any sound, any speed faster than that of sound is going to create a shock wave trailing it. And on this picture on the right side, this is actually a photograph of a high-speed bullet creating a shock wave. You can see here, this is the front and this is the back, okay, of the shock wave. So here the pressure is higher than usual, and in this region the pressure is lower than usual. And anytime you have variation of air pressure, it's a sound. It's a sound wave that you're going to hear. And this angle will help you determine how fast this bullet travels. And if you make a measurement of this angle with a protractor, you get about 32 degrees. And then we can calculate how fast the speed of this bullet is, okay? Because I have sine theta equals V over Vs. And that equals sine 32 degrees, okay? This tells me what Vs is. So Vs would be equal to V divided by sine 32 degrees. And you do that math, you find it roughly equal to 1.9 V. Okay, so the speed of the bullet in this case is about 1.9 times the speed of sound. So we can also say Vs equals 1.9 Mach. What does Mach mean? 1 Mach means the speed is equal to that of sound. 2 Mach means the speed is twice that of the sound. Okay, so this is 1.9 Mach. Again, you can get that from the angle. All right, now let's look at a phenomenon that is associated with the shock wave, but it's not just about the shock wave, it's also about the moisture in the air. It creates a spectacular effect when when a supersonic jet travels at a through the sky at again a supersonic speed, but when there's enough moisture in the air, then as you watch these airplanes passing by at supersonic speed, you will see a cone like this. Okay, it looks like it's made of a triangular shaped white cloud. It's actually more like a cone shape. It looks like it creates its own white cloud trailing it. What is going on here? What's the physics? Well, you need two things here. One is this thing has to travel at supersonic speed, so there's a shock wave. And secondly, the medium, which is in this case the air, has to have enough moisture so you can have water droplets. Okay, and how come these two conditions, supersonic flight and enough moisture in the air, creates this phenomenon? What is the stuff? What is this white cone made of? What is the stuff inside that appears to be white? Well, we can actually watch a little video. You can actually see this this phenomenon, and you will get you got a good explanation of that as well. Okay, so let's see. We open that up, and we can actually watch it.
San Diego, California, October 2010. A fighter jet roars across the sky. Suddenly, there's a burst of white surrounding the wings. The crowds watch in amazement. This isn't an engine malfunction, and the jet isn't about to explode. By slowing the footage down, this amazing vision becomes clear. As the plane approaches the speed of sound, it is momentarily engulfed by a blast of cloud. This is strange weather at its fastest. Meteorologist Steph Golter explains exactly how this bizarre cloud is formed.
To form a sonic boom cloud, you need two things really. You need a lot of moisture in the air, and you also need a plane traveling really, really fast. As the plane is hurtling along and getting faster and faster, the air ahead of the wing is all becoming really compressed, but behind it is all stretching out, and that allows the pressure here to drop. That allows the air to expand, and as it expands, it cools. And that cooling allows the water vapor to condense. And that's why the cloud forms.
It's the sudden change in pressure from high to low that creates this cloud formation. Steph demonstrates exactly how this pressure change works.
We can imagine this to be our atmosphere then, and inside we've got some air and we've also got some moisture as well. Now we can pretend that this is our atmosphere around the plane, and we can show that going from high pressure to low pressure creates a sonic boom cloud. Now, I've only got two hands, so I'm going to need a little bit of help in order to make the pressure here a lot higher. Now, this is what happens ahead of the wing. The air is all being compressed, but suddenly, as the air passes over the wing, the high pressure goes to low pressure, and you've got a cloud.
Former Navy fighter pilot Pete Ross.
So there you have it. That's an interesting video that demonstrates the this interesting phenomena. It certainly has to do with the sudden change in pressure due to the shock wave, and also the moisture in the air becomes the source of that water vapor. All right. So this is our discussion of chapter 17, sound waves. And in the next chapter, we'll continue to discuss waves, especially what happens when you get more than one wave source present at the same location. And then we have to add all these together. That is called superposition of the wave. And we see new phenomena associated with that. That's in the next chapter.